So hello everyone, welcome to Prep for IISER, and this will be the first lecture of your inorganic series. In inorganic you have 4 chapters: periodic table, chemical bonding, coordination chemistry, and DNA block. This is your first lecture. This is the periodic table. I will guide you through the inorganic section. So in this video I will cover the basics to the required concepts for IIT 2026 or 2027, doesn't matter. And in this lecture I will cover the theories with examples, and I will not recommend anyone to see this lecture if he or she is a first time learner. This will be for your revision. You can look for it. Okay, so let's not talk about much and let's start. So first we check our syllabus. There is the genesis of periodic classification, modern periodic law, present form of the periodic table, electronic configurations, periodic table and the types of elements as PDF block, periodic trends and properties in elements. Okay, so I took all the materials I am going to use in this lecture from NCERT. You can just look for it, and I will start from the genesis of periodic classification. After that, Mendeleev periodic table, modern law periodic table, the trends, some facts like length and contraction, electron gain and enthalpy, and I will cover till up to the oxides. Okay, so I hope you all are ready. So let's start. So let's start with the Dobereiner triad. The Dobereiner triad, what Dobereiner told, that you have 3 elements A, B, C. Their mass is Ma, Mb and Mc. So the relation will be M of C will be equal to M of A plus M of B and their average. So this is how he designed the periodic table. For the first one, he used this triad Li, Na and K. Okay, he used these 3. So if you check the mass of lithium plus mass of potassium will average out nearly the mass of the sodium. Okay, this is the Dobereiner triad. I am not going to spend a lot of time on this, okay, because we have more things to do later. So let's go for the next one. The second one is your so your next is Newman's octave. It takes the inspiration from the music, like as you have now, sa, re, ga, ma, pa, dha, ni, and then sa comes again. Okay, so Saptashur, what we have told it, like there are 7 there are 7 notes, and the 8th note is repeating again. Okay, so if we like it like helium, lithium, beryllium, boron, carbon, nitrogen, oxygen. Just let me space it out a bit. Nitrogen, oxygen, fluorine, sodium, potassium, magnesium, aluminium, silicon, phosphorus, sulfur, INFCl, the rest of it. As you can see, if you mark the number 1, 2, 3, 4, 5, 6, 7. The eighth one is repeating again with number 1. Okay, so this is what Newman told. And as you can see, the LA, NA and K, these three have same property according to him. And in the modern periodic table, we can also see that Li, Na and K are in the same column. Okay, so first one is Dobrandov triad, second was Newland's octave, and the third one, the most significant one till now, is Mendeleev's periodic table, whatever Mendeleev did. Okay, so as you can see from the previous two model, rather than previous two model, this model is much more defined, well structured. Okay, he divided it into groups and series. Okay, he told it group and he told it series, and each group is divided into two parts. Like see, in group 0 there is helium and neon. It is divided by hydrogen. Here is lithium, here is sodium, as you got the idea. But what Mendeleev used mainly to design this periodic table, that is one fundamental law. Uses this function, he uses this law, like periodic properties of elements. This is what he used. Okay, so how did he do using that? Cause the periodic properties of elements are actually a periodic function. This is function. Okay, so this is what he used. Periodic properties of elements are the periodic function of their atomic masses. This is the main idea he used for designing this periodic table, and now we will see that how he succeeded in this, and this have a few demerits also. We will also discuss on that. Okay, so this is your Mendeleev periodic table. As you can see here, there are eight groups and 12 series. Okay, you can see it from here. For this periodic table, there are few things wrong with it. Okay, so the first thing is, as you have already noticed, like according to the law, it is the periodic function of atomic weight. Okay, that we can that means that the elements are placed here on the base of atomic weight, right? But there are a few errors. If you can see iodine and tellurium, the mass of iodine is 126.9 and this 127.6, so the tellurium should be later and iodine should be prior to it. This is the first demerit. The second one, so this is the first demerit. In the demerit, there is same atomic weight but different position. You can check this one. cobalt and nickel. Both are 59, but their position are different here. Okay, as you can see it, the second one, their second one is position of isotopes. The third major one is position of hydrogen. Okay, as you can see, the hydrogen here, he cannot determine the proper position of hydrogen. He sometimes keep it in the group 1 and he sometimes keep it in the group 0. So this is the main difference. And the third one is same atomic number, different position. And the last one is your element placed before there, like this tellurium and iodine. Okay, so these are the demerits of the Mendeleev's periodic table, and in this periodic table he did an incredible job. Okay, so what he did, like with aluminium, he left a space. Okay, that is gallium here. Then gallium was not discovered till then, so he kept this place empty. He named this place as just let me do that. So he kept four like this places. One is your Eka al Eka aluminium, Eka aluminium. Second one is Eka boron. Third one is Eka silicon. Fourth one is Eka manganese. He kept these four places empty, expecting that this element might get discovered in the future, and it does. So this make Mendeleev's the first person to make a proper periodic table. So the Eka aluminium is now known as your gallium. Eka boron is currently known as scandium. The Eka silicon is currently known as germanium, and the Eka manganese is currently known as technetium, Tc. Okay, so these are the four things that he left in the periodic table. Like this gallium was not there, the boron, the scandium thing was not there, the scandium thing is not there, germanium was not there, and technetium was not there, but these are all present in the modern periodic table. Okay, and before going into modern periodic table, I want to tell you a small thing, that is the Moseley's experiment that actually help us to prepare modern periodic table. So what actually Moseley did? Moseley did that he measures the X-ray, okay, the X-ray frequency X-ray frequency emitted by metal when it was bombarded by high speed electron. This is what he did. So he gave a simple law. From here we can derive two plots. Okay, the one plot is root of a frequency by atomic mass, and the second one is frequency by atomic number. So how this two plot looks, this is your root and this is your atomic mass. This plots kind of looks like this. Okay, this is your axis, this is your first plot, and the second plot kind of looks like this one look slanted like this is your sigma root of your root of frequency, and this is the z your atomic number, which we indicate as z. These are the two plots he provided to us. With helping of this we make the modern periodic table, and now I will tell you how the modern periodic table actually is. This is a modern periodic table. You have already seen this. I do not have to tell, like it has 18 groups and 7 periods, like 18 rows and 7 columns. The most fascinating thing, or its basic difference against Mendeleev periodic table, is Mendeleev use their periodic properties as a function of their atomic weight, but here we use their atomic number, which we denote as Z. This is the main thing which makes it different and more better than Mendeleev's periodic table. Now, if I just tell you a brief that how this periodic table looks like, this is your S block, like this is your D block, this is your P block, and this is your F block. Sorry, the P block include this one too. My bad. These are S, P, D, and F block. These are all four. It is divided into this four. Now, if I tell you more about it, if you need, this row is called as halogens. This row is called as chalcogens, and this one is called as pnictogen. You don't need this actually. Okay, you mostly need this division S, P, D, and F. Okay, so and let's talk about what we call to this first one. We call it as alkali metal. This one is alkali earth metal. This one we call as transition element, and I told you this this is the pnictogen family, this is the chalcogen family, this is the halogen family, and this is the inert. And for F block, this first row is your inner transitional element, and this second block is your inner transition element. These both are, we call this a rare earth metal also. Okay, so this is the overview of our modern periodic table and how this periodic table is formed, and let's look a bit in depth with it. So before going in depth, as you can see, our periodic table total has 118 molecules, sorry, my bad, elements. Suppose after 118 after a few years, one of you discovered the element which will place in 119. How will you name it? So for naming it, IUPAC gave us this structure. We'll give it. So you discovered 119. As you can see, if your digit is 0, you will name it nil, 1, un, bi, tri, quad, pent, and so on. So if your element is 119, what you will name is for 1 it is un, second one it is un, and for 9 it is n. So it is un and n. How will it look like? It will u. This will be your element. Suppose someone discovered 123. So how will you name it? Using the same 1 for un, for 2 it's by the. So it's u. Okay. So I hope you understand this, and so let's proceed further. Now suppose I gave you a random element and I ask you to determine its position in the periodic table. How are you gonna do it? Let me show you. Actually it has two methods. I am showing you the one I use mostly in my days. So suppose the number of elements is 51. Okay. So all when you are doing this, always keep mind this this section. This will be your guideline. So as I gave you 51, the nearest one of the nearest noble metal of your element is this one, 54. Okay, and now you already know this, like you need 51, your nearest is 54. Do you know in which one 54 is? No, right? You might not know. So do you know that 54 in which period? You may not know that. So for this, you have to keep in mind this. This belongs from your first, second, third, fourth, fifth, sixth, seventh. So 54 is in your fifth period. Okay, you determine the period. And now, as you can know, your last one is your noble metal. The previous last one is your halogen. Then one is chalcogen, then one is pnictogen. So this will be 54, 53, 52, 50. So your pnictogen is your group 15 element. So this is your group, this is your period. Oh, period. Okay, and your block is P block. So this is how you can determine the position of your element. This is a very mechanical way, and sometimes you will be given some elements that you cannot do using this because you can't always count back, right? For that there is a standard method for doing this. This one is using the electronic configuration. I am not teaching you how to write electronic configuration. You will learn this in your atomic structure. I hope your physical chemistry faculty have taught you already. If you didn't, he will. Don't worry. Okay. So suppose you are given bromine. As you know, bromine is the 35th element. So boron's configuration, if I write, so 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p. So always check this bigger one. As you can see, your principal quantum number here is 4, so it will be from group 4. You get one clue. The second one is its period. For the period, as you can see, you have 10 plus 5. Okay, so you have 15. Group 4. Okay, and now just remember one thing. One thing to do this. This is to determine your period. Okay, as you can see, the S is 2 and 4p here is 5 and here it is 10. So if I summation all this is 17. So this is period number 70. This is the whole information you need about the bromine or the position group 4, 17. If I show you the periodic table, as you can see, yeah, here is the position of bromine you have calculated. So I hope now you know how to calculate the position of elements if there is your electronic configuration given or not. Okay, so let's jump on the second topic. So this one is called effective nuclear charge, as you may have studied, I hope so. Atomic number minus alpha. This one is your formula. This Z is your atomic number. This sigma and this one is your screening constant, and this one is a Z effective, which is basically Z effective is your effective nuclear charge, ENC. So now ENC act, there is a trend. This is your trend for it. As you have know, D and F, their Z value is much higher. So these two are called as pore shielders. And to give you a better understanding what a nuclear charge is, suppose this is your nucleus and these are orbitals there. Okay, and there is one electron and there is another species, this is a nucleus, and here it is the electron. So when this nucleus is attracting this electron, these all are shielding it. These all are shielding it. So it cannot pull it much harder as it want to. But here you have just two orbitals. It can push it. It can push it much harder. So these are a good shielder. Okay. So after that, the next topic is your atomic radius. As you might have known, as you can see in this table also, like here you are going across the period, like when you go from left to right. Here is 152, here is 111, here is 8887. So we can tell that it is decreasing, right? Across that it's decreasing. And you can see in this one too, this one is also in decreasing. But here is a simple case that a noble metal from any period is the biggest. Like it just reducing, and suddenly the noble metal appears and it is the biggest one among them. Okay, as simple as that. So let's go from top to bottom. As you can see, 152, 186, 231, 244, it is basically increasing. And if you see this one is also increasing. So this is your basic trend for your atomic radius, right? You can see it from here. This is the atomic number and the radius. The lithium is the biggest one, beryllium, boron, carbon, nitrogen, fluorine, neon, and suddenly it will take a peak. That will be a neon. As you can see, this one and this one we see it in the previous chart. So let's talk about some other groups too. Let's start with group 13. In the group 13, if you see, there are boron, aluminium, gallium, indium, Ti, and NH. In group 13, you may expect it boron, aluminium, gallium, indium. So you may expect it to be like this, right? Because it's down the group, but it does not hold here. The correct one here is this one: boron, gallium, aluminium, indium, tellurium. This one is your correct one. Okay. In terms of group 14 and 15, this law holds. Like if you go down the group, the size will increase. This one will happen. And for group D, like for group 3D, there is again a thing. The group 3, Scandinavian science teacher Vinita Kumar Manfeko Q. So if you see, like if I put it in that trend, SC, TI, V, V, Cr Mn. Okay, the Mn took a huge jump here. If I show you the plot, it will be like this. Here is your NM and here MN and here is your SC. You can find it in the NCRT also. In the NCRT also. MN, and after that, just let me write here, it will be better for you. SGT, VR, CR, MN, ferrous, chlorine and nickel has pretty same. And again, there is Cu and Zn. Because after this plot, kind of go upwards. This one is zinc, this one is your copper, nickel, cobalt, ferric, manganese, chromium, vanadium, titanium, scandium. Okay, so keep this one in mind also. I have no idea if you can see it or not. Just let me mark it with a red. And this one also. For 14 and 15 it remains same. And why this happens? This one is happening due to that shielding. Okay, these all are good shielder, but when it's come to Z and Cu, and there is a small subsection of it, it is called the in the D block. What happened? That 3D, 4D, 5D, and if we talk about their shielding, 5D is a much poorer shielder, 4D is a little better, and 3D is better among them. Okay, so if we write it there, 3D is always 4D, but it's kind of equals to 5D. Okay, I hope you understand. This is all your everything about atomic radius. Did I miss anything? Just let me recall it. Now there is a phenomena in your lanthanoids. What is the lanthanoids and actinides? If I show you, this family is your lanthanide. Lanthanoids. This is called a lanthanide. In the lanthanoid, there is a interesting thing happen. It is known as lanthanide contraction. The lanthanide contraction happens as you go from left to right. The size should decrease. The size should decrease from from left to right, but here in middle there is a element called europium, EU. It holds the biggest atomic radius. So it will be like, first there is EU, then it starts with CE, PR, and dot, dot, dot. This one. For LA, to put the EU at the first, then it starts that CE, PR, ND, PM, and dot, dot, dot. Okay, I hope I can help you to understand what is lanthanoid contraction. The lanthanoid contraction is happen basically whatever I told you in the first. It is the 4F series. The 4, due to 4Fs, they are very poor shielders. That's why their size starts to decrease. And in middle there is EU. It will jump forward and it will continue like this. Okay. Your next topic is your ionizing energy. What ionizing energy is? Suppose there is a element. You have to first convert it into gas, and after that you extract one electron from it. So when you have an element, you turned it into gas and take out for one electron from its valence shell. The energy you need to put in that to pull out that electron is called as ionizing energy. Okay, and this ionizing energy, like this will be your IE1 when you take the first electron out, and after when you take the later one, it will be your IE2. Sorry, I am just writing it a bit wrong. Like your like pulling the first electron will be much easier. When you pull the second electron, you have to put a little more energy. When you want to pull the third electron, you need to put a little more energy. Okay, and this dot dot dot. So that means the taking out the first electron from your valence shell is easy. But when you go deeper into the shells, it will be harder for you to pull out more electrons from that. Okay, and for the trend here, as you can see, hydrogen, helium, lithium, neon. So LINAKRBCS, this all are top to bottom. As you can see, from top to bottom, the ionizing energy is decreasing. Okay, and the factors which are controlling ionizing energy, first one is size. If size increases, the attraction between the nucleus and the outermost shell electron gets weaker. So the ionizing energy becomes weak. This is the first one. And the second one is when your Z effective increases, the attraction will also increase. That will help you to get an increment in the ionization energy. These are the two factors, two ways to determine the ionization energy. Now, can you speculate the ionization energy trend between the groups S, P, D, and F? In among four groups, the S, this will, because F and D are poor shielders, these one are good shielders. So taking an electron from S is much tougher than its P, and D and F just okay. And the trend in ionization energy, the trends of ionization energy, when you go from this side, the ionization energy increases, and when you go in this word, it decreases. Okay, and ionizing energy a bit peculiar in your D block. Okay, so how it looks like for the group 13, if I see germanium, it's not germanium, it's gallium, my body, it's gallium. Okay, so we are going down the group. We expect it like it should be this, this, but it does not look like that. It looks something like this. boron, aluminium, gallium, indium, tellurium. Okay, keep this in mind. This one is kind of your next topic is electron affinity. I will teach you the inert pair effect first, then I will teach you the electron affinity. Okay, the inert pair effect is basically tendency to keep lower oxidation state. So this actually, if you go top to bottom, it increases. Let's take an example for it. BAlGain. Bromine, it shows +3. This it shows +3. Gallium +3 and +1. Indium +3 and +1. And the tellurium +6 +1. This one is the lowest. These two also have +1, but they also share +3 too. +3 also. So the tellurium has the highest inner pair effect here. So this one increases. Okay, now let's come to the second part. It's electron affinity. It is actually the opposite of ionizing energy. When you have an element, you turn it into the gaseous state and you want to put an electron into it. The energy you required to do this, you need some energy here, right? This one is called as electron affinity. And if you follow the definition, electron affinity is naturally a positive energy, but you have to put a force from outside. This electron affinity will be in negative. Okay, you get this 2 point. And just keep one thing, if the electron affinity is positive, okay, it's exothermic, and it's negative, it's endothermic. Okay, did you understand?